In this video, we'll describe the operation of a discrete convolution, which will be used for computing the forward propagation in a convolutional neural network. So I mentioned before that when we're computing the pre-activation of a hidden unit, what we'd be doing is that each hidden unit would be segmented into different feature maps. And then for each feature map, I mentioned at the last video that we would actually perform a discrete convolution operation. This discrete convolution operation would actually give me the pre-activation that comes from each of the ith channel. So performing this would correspond to, for each hidden unit, multiplying its weights with its receptive field and then summing the accumulated pre-activation. And then we'd sum also over all possible input channels. So that would give us the pre-activations of all the hidden units in the same feature map, and then we could apply some nonlinearity to get an activation. And so now in this video, we'll look at the specific definition of this convolution operation and how it relates to computing pre-activations in the feed-forward neural network. All right, so let X be some input image. So it's going to be a matrix. And K is going to be a kernel, and it's also going to be a matrix. So notice here, I'm not using my usual notation of using capital letters in bold to refer to matrices. That's just because I'm trying to stick with the notation of Jarrett et al. In their paper. I want to sort of look back at the original paper and be able to relate the notation I'm using with theirs. But normally I would use capital letters. So just don't forget that this is a matrix and that's a matrix. So if you're performing the discrete convolution of that image X with some kernel K, we will perform the following computation. So the convolution of X with K, that's going to yield a matrix as well, an image. And at position ij, so it's the ith row and the jth column in that matrix, we'll have the following value. So what we'll do is that we'll sum over all offset possible, where the offset P and Q range between 0 and R minus 1, where R is the number of rows and the number of columns of K. So we're assuming the kernel is a square matrix. So for all possible offsets, all combinations of these numbers here, we'll look at the pixel at position I and J, but offsetted by P and Q, and we'll multiply that by the element in the kernel matrix at offset P and Q, but where now the offset is taken with respect to the bottom right corner of the matrix. So if I have a matrix for my kernel matrix, which is 3 by 3, and say I have P equal 1 and Q equals 0, then it means that the element K, R minus P, and R minus Q, where R is 3, P is 1, and Q is 0, would correspond to essentially counting and relatively to the bottom right element of that matrix. So I would be at row 1, that's, sorry, it's the second row, so that's R, which is 3 minus 1, which is 1, so that's 2. And then I would be at R 3 minus Q 0, so at the third column, so this would be that element. So with offset 1, 0, instead of being this element here, we're counting, if we were counting relatively to the top left corner like we would normally do, when we're accessing elements in the kernel, we're counting relatively to the bottom left corner of the matrix. So that in this particular example, it would be this. So in this sum, we're doing over all possible offsets, where P would be equal from 0 to 2 for R equals 3, and Q would be 0, 1, or 2, and we take all combinations. And so in each case, we multiply the element at offset P and Q at position I and J in the image, and multiply it by the corresponding element in the kernel matrix. So that's for the mathematical definition. Now let's look at visually what this computation corresponds to, and it's going to be much more intuitive once we do that. So we can think of this operation as first taking the kernel matrix K. So here's an example of a kernel matrix, a 2 by 2 kernel matrix. And then what we'll do is that we'll flip the rows and the columns. this will do is will make everything more intuitive, where we won't have to compute the offset with respect to the bottom right corner, but instead we'll compute the offset with respect to the top left corner of that flipped matrix. So this matrix, so I'm going to use tilde for like the operation of flipping the rows and columns. It would correspond to that matrix here. So we see we've switched the rows and we've switched the columns with respect to that matrix here. Okay, so once we have this k tilde, what we do is that for each position where we can fit that kernel, we do an element-wise multiplication of all elements with the part of the image that is at the current at any given position. So in this example, we're starting at the top left corner. So ij, this would be for the element I equal 1, j equals 1. So we do this element-wise multiplication, and then we sum. So we have 1 times 0 plus 0.5 times 80 plus 0.25 times 20 and plus 0 times 40, which is here. So that gives us 45. And then we continue this, but for all values of I and j. So for all positions where we can position the top left element of the kernel matrix in the image. So then we perform the same operation, element-wise multiplication, and then summation. Element multiplication here, here, and here. So all of these terms. And then summation of all these 4 values. In this case, this gives 110. And we continue like this for all positions. And that gives us the convolution of k with this 3x3 image here that I made up for this example. And so notice that here I'm using some sort of gray color coding or illustration to sort of illustrate the intensity of the resulting image. So we can sort of think of it as visualizing it as an actual image. So we notice that this operation, this convolution operations, where we're taking a kernel and we're placing it in all positions in the image, and then we're doing these element-wise multiplications with a sum, that's very similar to the types of operations we have to do when we're computing pre-activations in a feed-forward convolutional neural network. And it turns out that indeed we can convert what I described as the way we compute pre-activations using this with convolutional neural network kind of connectivity between layers using a convolutional operation. So so actually the pre-activations that are going to be computed from channel xi in order to compute the feature map yj, where yj would be after the nonlinearity here. I could compute that part of the pre-activation by just deriving a convolution kernel, which is just going to be my connection matrix wij in my convolutional neural network, and then flipping its columns and rows. Okay, and that will become my convolutional kernel. So that when I'm applying the discrete convolution, then as we've seen in the description I gave before, I'm going to be reflipping the rows and columns, so I'll get back to the actual matrix wij. So from that kernel, then to get my pre-activations that are computed from the ith channel, I just perform a convolution between the ith channel, so this slice in this image, if I have multiple channels, with the kernel kij. And then to compute all of yj, then I would sum the result of these convolutions across the input channels, and then I'd apply some nonlinearity, and then that would give me the activations of that particular feature map. And to get all the feature maps, then I would do this for all values of j's, for all feature maps I have in my neural network. All right, so it might seem complicated that we would, have this operation where I have to flip columns. Like I said, columns and rows. Like I said, for one thing, I'm mentioning this connection because that's where the name convolutional neural network comes from, and also because you might have access to a library that computes convolutions very efficiently, in which case you want to do this transformation. There's another type of signal processing operation known as the correlation, which actually corresponds to doing the same, essentially what I've described before, but without flipping rows and columns. So it would be exactly the discrete correlation between xi and my matrix of connections. And so there's a relationship here again between the discrete correlation and the discrete convolution, which I won't get more into besides just saying that it's essentially the same thing without the row and column flipping before we do the element-wise multiplications with the sum at every position where we place the kernel. But so from this, it means that now we have, if we have some efficient code that do convolutions, then we can compute all of my pre-activations and compute all my feature maps fairly efficiently. So to get an idea of the kind of the result of applying these discrete convolutions, or computing pre-activations between some input channel for some JF feature map. So imagine that I have a matrix Wij which corresponds to this matrix here, where I have zeros on the diagonal and 0.5 on the other elements. So in this case, it simplifies everything because flipping rows and columns is exactly equivalent. It gives the same matrix. But if I were to do this discrete convolution on this image, then I would get this contribution to the pre-activations of that particular feature map. And we see that we have a fairly high value at places that correspond to regions of the original image where I had a pattern that is similar, sort of like this with a kind of a diagonal edge. So we have 255 that corresponds to this superposition here of the filter or the kernel, and then 255 again where I had this value here. And so I see that once I've computed this, I already have some illustration of where do this particular kind of feature with an edge with that angle is present in the image. And then the idea is that with a nonlinearity that we have in a convolutional neural network, that we might be able to emphasize whenever this value of correspondence between the filter and a particular region of the image, so emphasize when it reaches a certain threshold. So in particular, if I were to apply this element-wise nonlinearity on the feature map pre-activation, assuming we have only one input channel, so for instance, by multiplying 0.02, the result of the convolution is subtracting 4 and passing this to a sigmoid, then I'd get fairly close to 1 values in the part of the image that has this particular kind of pattern, and everywhere else something closer to 0. And that's the kind of feature detection that a convolutional hidden layer is going to do. It's going to be able to detect certain type of features, and in a feature map, again, we'll have the same feature being detected everywhere in the image. A final notion related to convolution is the idea of zero padding. It's going to be useful in particular when we talk about computing the gradients, when we're going to be deriving the procedure for computing gradients with respect to some loss, for instance, the classification loss that we've been using in regular neural networks. So essentially a procedure for backpropagating gradients across the convolutional neural network. Zero padding is when we allow to go over the borders by essentially padding zeros everywhere around the image, enough so that we can fit our filter everywhere as long as there's at least one element from the filter that or the kernel that overlaps with the original image. So in this case, by adding, if I add zeros here, so one row of 0, and I have a filter which is the same as before, which is just 2 by 2, then this way I'm able to fit the filter in the position where it overlaps with just one element here. There are other types of padding. We can do a kind of reflective padding where we would act as if there were like a mirror here, and then so the value here would be 255, and the value, if we were to pad here, would be 0 because it's 0 here, so a sort of symmetric kind of padding. But zero padding is probably the one that's most used in convolutional neural networks, and that's the one I'm going to be referring to whenever I'm adding this underline notation here with a convolution operation. That's the one that we're going to invoke in particular when we talk about gradients. So if we do the convolution with the same kernel as before, but with zero padding, then we get this convolutional output instead. And we know this that because we're able to fit the kernel in more positions now, we get a larger output, a larger matrix after the convolution. Okay, so that's it for discrete convolutions.